Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali Muqaibel. Today's lecture is about satellite subsystems. Satellites are very complex, extremely expensive, and they cost a lot of money. $125 million on station, several millions dollars per year. Of course, those numbers changes with time. But they just give us a rough estimate about the cost of satellite systems. So, what are the satellite subsystems? Let's start by stating them. While enjoying the view from the geostationary satellite, a geostationary satellite would see the Earth like the one that you're seeing in the picture right here. So the satellite subsystems, the first subsystem is the attitude and orbital control system. Attitude and orbit control system, AOCS. Then we have the telemetry tracking and command, TT&C. And some are using TTC&M, which is telemetry tracking, command, and monitoring. Then we have the power system. Number 4, we have the communication system. And then we have the antenna, if you like. And finally, we have the thermal control system. We will not spend a lot of time on the thermal control system, but we'll shed some light on these subsystems to have an idea before we indulge into the communication part. So the attitude and orbital control system consists of rocket motors and is needed to get the satellite in the correct orbit. As the name says, it controls the attitude and the orbit. So it is needed to get the satellite into the correct orbit and keep it there. So we call it orbit control. And it keep it there at the time of orbit insertion. When we start the process, when it goes from the satellite, from the rocket, orbit insertion, orbit maintenance, and even fine pointing. So orbit insertion, orbit maintenance, and then the fine insertion. The major parts of this subsystem, we have the attitude control system and the orbit control system. The orbital maintenance, I'm just highlighting these two in blue. For example, for the geostationary orbit station, or a satellite in the geostationary orbit, keep burns about every 4 weeks. And in every 4 weeks, there will be a deviation by plus or minus 0.05. So we need to recontrol or to maintain the orbit by burning fuel, by turning on the motors in the right direction. Recent approaches use different thrusters, crooked, and we could have one on the east-west and north-south, so we have control in different directions. Then we have the fine pointing. There are two principles forms of attitude stabilization to control. So this is called the body stabilized, the spinners. These are the ones shown here. The satellite spins in a certain speed and so on to maintain the right direction. And we have the 3-axial system stabilized, which is the one shown here. So an example of that is like the Intelsat. And also here we have the system which is Intelsat 5. So these are different types of satellites. The body spin or the spinner, because it spins, and we have the 3-axis because it has clearly like extends in different axes. Now, if it's important to clarify these axes, so we define the axis system. If we have the satellite here and we draw a line that goes through the subsatellite point pointing to the center of Earth, then we call this angle that rotates around the axis tangent to the orbit. This is the orbit here, and this is the blue line shown as tangent. Then this is called the roll axis. Okay, and we will control north and south. And also we have the pitch axis, and that's the line move around the axis that's perpendicular to the orbiter. If this is the orbit and here's the Earth, this is the line. and this is called pitch, and this is controlling the east-west maneuver. And also we have the yaw axis, so moves around the axis that's pointing to subsatellite point. So those terminologies are known to the satellite specialists. Now the second subsystem is the telemetry tracking and command, TTC. So you can see that we have the satellite. There is satellite TTC&M antenna, an antenna that's used for telemetry tracking and command. So it communicates with the earth station. We have also a telemetry receiver and tracking system. So we receive the data, we process them, and we send the commands to control again. So we receive the data, we process them, and we have also the transmit antenna for the TT&C, and we send the telecommand transmitter. So partially on the satellite and partially on the earth station, reporting spacecraft health, temperature, pressure, whatever can be measured. And then we have the monitoring commands action. It also determines the orbital elements. So remember, we have the 6 elements. It sends the data to the tracking system, and we have launch sequence deployment. And this is during the launch process. The TT&C system will also work during the launch, like opening, if there's mechanical extension of antennas or movement or so, it will be controlled by the system. We also control the thruster to adjust the orbit, control of payload communications, and also we have the TTC&C. We also, as I mentioned, we call it TT&C or TTC&M. Is often a battle between operations and engineers. You know, the operators would like to know everything, so they want you to send all the data, all the temperature and so on. However, engineers who worry about communication and bandwidth wants to just minimize the requirement to a minimum, just reduce the cost. So in the telemetry tracking and command, we can define different functions like this. We say that telemetry means monitor all important temperature, voltages, current sensors, transmit data to Earth, and record data at TT&C and M stations. For the tracking, we measure the range repeatedly, can measure Doppler shift also, and also compute the orbital elements. And also we do the planning for the maneuver and communicate with the main control stations and users. For the command, a secure and effective command structure is needed. Backup and redundancy are very important in this case, because you don't want somebody else to control your satellite, and you also don't want to lose the control. During the launch sequence also, we have switch on power, deploy antennas, and point antennas to the desired location. While in orbit, we'll need to send command to maintain spacecraft thermal balance and control payload, thrusters, and what have you. Telemetry, measurement, tracking, and then control and sending the command. So for the power subsystems, the power uses solar cells are used for the communication and housekeeping, and solar cells are having an apolity so that we can measure how much power they produce per meter squared. So we have 1.39 kilowatt per meter square, and this is available from the sun. Of course, these numbers are usually for geostationary Earth orbit, and of course they could change depending on the efficiency of the solar cell. Usually cells have efficiency on the range of 10 to 15 at the beginning of life and their use. Of course, these numbers have improved these days. We can get 18, 19, and as the technology improves, these numbers changes. Solar cells output falls when temperature rises. So we expect that as the temperature increases, the performance will become less, although they are solar cells, but they need lower temperature. So that's about 2 millivolt per degree centigrade. 3-axis hotter is less efficient than a spinner in that case. And we have also the solar cells can be redirected for better sun exposure, so we can control their directivity, and they can generate up to 6 kilowatt from solar cells in total. As I mentioned, these numbers are subject to technology, so we're just presenting them to get used to the units and so on. Otherwise, the exact numbers, efficiency, I'm sure that they have improved dramatically. For the batteries needed during launch, the launching process, during the eclipse, because there is no source of solar cells, and the different types of battery used. We have different chemistry used, or different material used for building the batteries. We have also typical voltage generated between 20 and 50 volts, and the capacity 20 to 100 ampere hour. Remember that ampere hour is a unit of energy. It's not a unit of it's a unit of energy, not a unit of current. Ampere hour. Okay, it's not a unit of power, it's a unit of energy. Batteries are conditions before each eclipse, so we need to control the condition. So we could discharge, charge. We have smart controls that we make sure that we extend the life of the batteries. So we discharge them, and then we charge them before the eclipse to make sure that the charge is sustainable. For the command subsystem, the primary function of a communication satellite is, for the communication subsystem, the primary function of the communication subsatellite is the communication. So everything before and after is just to serve this subsystem, where usually we have the main source of revenue. And this is, when we design a system for communication, we would like to maximize the traffic capacity, the data rate capacity, the number of users that can be served. We have usually a downlink from here, from the satellite to the earth station, and we have the uplink. The downlink is really the critical one, because we have here we can have whatever power we want, but here we are limited power and limited antenna size because of being in space, so we cannot send anything there. Early satellites were power limited. However, now most of the satellites are bandwidth limited. So we have two types of communication in principle. We have the pent pipe, as if you have pent pipe, where you have a pipe that communicates. Then it's a bent pipe that just bend the data. So we have going up, going down, amplifies the received signal and transmit to a different frequency, usually lower frequency. Usually the downlink is lower than the uplink. We want better propagation, and we have a limitation here. We also have baseband processing transponders, where we take the data, process it, do some processing, and then send a different data or related data. So either we just take and reflect, or maybe we can do some processing in the satellite. So we have bent pipe and we have baseband processing transponder. I'll leave it for you to write in the comment section what's the difference between transceivers and transponders. So write your answer in the comment section, please. Now, this is important to mention that the number we give just as examples, but there's a growth in weight and technology. So this diagram shows you, for example, as we go on time, the trend of being larger, heavier, more costly, and much greater capacity. But now maybe we're going into the opposite direction. So we have now satellites that are back being small. When we compare Intelsat at different versions, you can see that we're looking at the year of launch, dimension, on-orbit weight, end-of-life primary power, total bandwidth, national capacity, two-way telephone circuit. For example, this is handling only 240 telephone lines. This could handle 33,000 plus 2 TV channels. Or, of course, you can replace the TV calls with TV channels. Design lifetime. So they were short span, and now we are extending them. Okay, remember that they need fuel for maneuvering. Spacecraft cost, okay, is increasing. I'm sure now we have different trend. Launch cost, cost per telephone circuit. You can see the huge reduction. And then we have the contractor, the companies that are working there. Okay, for the communication subsystem, for geo-Earth orbit, received power rarely exceeds 10⁻10 watts. That's a very limited power. But what's important, even if we have small power, what matters is the signal to noise ratio. So even if the power is low, if we have sensitive device and small noise, we can still make use of it. Signal to noise ratio from 5 to 25 dB, because the noise itself is made very small. And that's the range of useful received signal level. We use directional beams to focus, so we can have spatial frequency reuse. So we point, for example, our antennas to Saudi Arabia or part of the Middle East. We can use the same frequency and different spatial location. That's called spatial frequency reuse, because we are using the frequency. We have also polarization frequency reuse. We have vertical horizontal polarization. We'll come into that later on. We now can define a transponder that consists of bandpass filter, a down converter to change the downlink frequency, and an output amplifier. So transponder is just kind of change the frequency and send, not like a transceiver where we receive the data fully and send again. The communication system has many transponders, usually 12 to 44, and some spare one. Of course, we have to keep some spare ones. When sharing the amplifiers, again, these numbers, as mentioned before, they're just for example, to give you an order of magnitude. But with the technology, they changes. When sharing the amplifier using frequency division multiple access, the power amplifier must be run below its maximum output power to make sure that we don't have intermodulation. You know that those amplifiers are nonlinear, which means they could give you product terms. So you remember that cosine times cosine give you cosine sum and difference. These are intermodulation terms, or cosine square give you 1 plus cosine double the angle. So whenever they have this squaring or multiplication, we get intermodulation. You don't want to get frequencies that are not intended. So if you operate your amplifier at high power, then you get nonlinearity and you get into troubles. The degree to which the transmitter output power is reduced is called the output back off. As if we're saying back off, reduce the power so that you don't get into this problem. Satellite antenna. If you want, this is kind of related to the communication subsystem, but we have, because of it's important, we have it separate here. We'll have a dedicated presentation for satellites, but for now, for antennas, just let's classify them into simple, where we have global beam of 17 degrees, low gain, low capacity. We have regional, where we can focus the beam into more, so typically 3 degrees into 3 degrees in both sides. And we have advanced, where we can point narrower, where we have narrower beam, can focus more into points on the Earth. We also can classify antennas into different shape: horn antennas, reflector antennas, and phase array. So for the case of efficient horn, they are efficient low gain wide beam. Reflectors, they have high gain narrow beam, may have to be deployed in space. These are general comments. Of course, a specific design will have its own characteristics. Phase arrays are complex arrays of antennas, electronically steered, and we'll come to them. As I said, this is just to give you an idea about the different types of antennas in terms of coverage, in terms of shape. But we have separate presentations for antennas. I'll be sharing them in the comments, or you can see them in my channel. Now, the diagram on the side shows you how the antenna get deployed, because this is how the satellite at the beginning gets separated from the rocket, and then we have solar array booms extended, then solar array panels extended, and of course then we have 30 feet reflector deployment of the antenna, fully deployed configuration. This is just one example. We have the antenna here. Now, one thing very important for satellite subsystems is we need to make sure that the equipment we have space qualification, because not all equipments are ready to work for space. You don't want to send an equipment and fails there at the top. They have to be very reliable. So there must be some measure of reliability. And remember that if you look at the reliability curve here, the probability of failure, this is the time. During the burn-in, we have high probability of failure. And then during normal operation, we have low probability of failure. And as we get towards the end of life, of course, the probability of failure increases. So launching and burning fuel in the beginning costs or make all equipment under pressure, just like landing, taking off and landing. So in between you have smooth operation, but with a certain probability of failure, but it become higher at the beginning and the end. So we have to use redundant. Let me show you an example of redundant configuration with traveling wave tube amplifier with double amplifiers at this stage. These are high power amplifiers. So we have splitter, and in case one of them fails, the satellite can be used without a problem. Okay, so when we look at satellite systems, we have to think about repeatability. So we can have different connection. We have cascade, we have parallel, we have repeated cascade, repeated parallel, and then we have also other ways for connection to make sure multiple redundancy, as we can see here. If you want, you can look at this diagram. This is the antenna, dish antenna. Okay, if you like symbol, we have the amplifier, low noise amplifier. We have also the bandpass filter. So it shows you that it only passes the signal in the middle, and it chops off the other signals. You have the oscillator, you have the down converter, another bandpass filter, and then we have another amplifier. And this is the splitter and the combiner. These are two amplifiers. So I leave you with this about subsystem. I'm sharing some practical numerical problems in my website. So please go to the link. They're fantastic problems to enjoy. And although we did not do numerical problems here, but they are there for you to practice. They use the common engineering sense. So I'll leave you with another question. Please write your answer down in the comments. In fact, how many satellites are there? At the time of trying to find the answer, there are lots of different answers. So some are saying that more than 19,000 satellites. There are fragmented distributed. If you search the net, you'll find totally different numbers. Please, if you can share with the numbers and justify them. Some will see 10,000, 12,000, 20,000. Some are active, some are dead. So please share your comment. Check the current number of active satellites and space debris right here in the comment section. Thank you for being good listeners, and we'll see you in coming videos.